Hi, I'm Peter Willis from BT's Applied Research, leading the software-based networks team. Today, I'm going to talk about the carrier challenges of autonomous networks. We'll be covering a few definitions about autonomous networks and network automation. We're talking about the importance of robustness. I'm Peter Willis from BT's Applied Research. Trouble with machine learning, a bit about experts and humans, and drawing up with a conclusion. So what is an autonomous network? It's a network that runs with minimum to no human intervention. Key solution to autonomous networks is using closed-loop control systems, which is a system that automatically regulates a process using measurement of the current state, comparison with the desired state, and adjusting the parameters of the system to minimize the difference. Examples include the adjustment of resources dedicated to a VNF to maintain low latency or traffic volumes vary. Synonymous with autonomous networks is network automation. For BT, network automation is a process of continuous improvement and evolution. It uses a lot of tools, and it's a long journey. Network automation is not new to BT. For example, Strowger is a 130-year-old technology that replaced human operators for setting up phone calls. To move on from where we are today towards the autonomous network, we have to ask, are we starting from the right place? Compare this to the evolution of the horse-drawn carriage to the automobile. The horseless carriage kept a lot of features that proved to be undesirable in the modern automobile. These are the features we don't require in today's networks that aren't appropriate for the autonomous network. When designing an autonomous network, the primary aim must be robustness. Efficiency optimization comes second. It's easy to optimize a network if we compromise robustness. A network must be robust to changes in the environment. For example, an increase in traffic due to home working due to COVID-19. The automation system itself must be robust for the network to be robust. It must be robust to changes in the scale or scope of the network and over time. Closed-loop control will be a key part of autonomous networks. And what side effects does the closed-loop control have on parameters outside its immediate control? For example, in the past, routing protocols could crash the router by using too much CPU, leading to a network meltdown. A positive feedback loop: as more routers died, the computational load increased, so more routers died. Even with extensive simulation, and simulators have a role to play in autonomous networks, often we need operational experience to understand all the side effects. However, there is a real risk of learn by doing with live networks. An autonomous network, or a closed loop within the autonomous network solution, will be performing optimizations, finding the best solution as the network evolves. But there will be external factors that beyond the scale, scope, or time frame of the optimization. For example, for OSPF, which optimizes network routing in real time, the externalities or external routes learned via BGP. Another example is if attempting to optimize a multi-layered network, and it may not be possible to optimize the optical network and the IP network at the same time, because these layers may be in different organizations or owned by different organizations. An IP network may use multiple different optical networks around the globe. Another way of thinking about externalities is to say we must recognize separation of concerns. Again, in network routing, it's easy to see the separation of exterior routing from interior routing. While generally, infrastructure management is separated from application management. Autonomous networks control system must be robust and must recognize externalities and separation of concerns in its design. Autonomous network solutions require extensive modeling. A model being a representation of the relationships, constraints, and operations of the system. The autonomous network solution will have multiple models in many forms of languages, not just machine learning models. In the RECAP project, which was a Horizon 2020 collaborative project addressing the automation of resource management networks and clouds, we had 6 models. User model, which modeled user behavior. Workload, which modeled essentially the traffic load. Application, which modeled how the applications work. Load translation, which translates the input workload to the consumption of system resources. And infrastructure, which models how much resources are available and where they are. The autonomous network will be dependent on APIs, and APIs are built around explicit or implicit models. So key things to note here are the models require domain expertise and modeling expertise to create. The models will need maintaining. Who is going to do that? The standards organizations, the carrier, the vendors, or the system integrators. But not one of these has the complete view. A vendor may understand the application and load translation, but not the workload. The operator may understand the users and workloads and infrastructure, but not the application and load translation. Models need maintaining because things evolve. For example, load translation model may need updating if the load balancing software is updated. If we had standard information models, it would reduce the amount of work required to introduce new components or services into the autonomous network. I'm less concerned about the actual language used to define the model, as we can cross-compile between languages, but more concerned with what the information is actually contained in the model. For example, what do we need to know about application to automate its installation and manage its lifecycle? There are many information models already standardized and ongoing work to create more. The question is, have we got too many that are incompatible and competing? Or have we too few with gaps in them? For example, it would be good if ONAP and ETSI were driven by the same models, noting the synergies between models and APIs. Part of an autonomous network solution may use machine learning, although many other techniques will be used as well. BT has developed some great applications of machine learning that are in use today, so I'm not anti-machine learning, but there are some well-known issues with machine learning. Machine learning cheats or finds shortcut learning. It can exploit shortcuts that may not work everywhere in the real world. Examples include the detection of pneumonia in X-rays. Machine learning used a hospital-specific metal token in the scan and the hospital's pneumonia prevalence rate and didn't learn much about pneumonia. For networks, this could imply if we bought in a system trained on another network, perhaps by a vendor, it may not work on our network. Machine learning may not work well if it cannot understand context, as in the call me an ambulance test. This means using machine learning to interpret human intent, as in intent-based networks, runs the risk of the intent being ambiguous without further context. It's also well known machine learning can reproduce human bias. For example, in network fault diagnostics, we can see technicians biased towards trying the lowest cost fixes first, rather than the most obvious fixes first. And this is the case where machine learning does something that is hard to understand, as in the famous case of the game of Go between AlphaGo and Lisa Dow in 2016, where the machine learning did something unpredictable that the human opponent couldn't understand. If we had a fault in the network and we couldn't understand how the network got into that state, how can we fix it? There are some increasingly well understood issues that must be addressed if using machine learning. How is the model trained? For example, faults may be external to our system and we don't see the data. Is your training data biased? For example, is some telemetry filtered out? When will you need to retrain? External events may render training data invalid, e.g. a code update. And there's a really good checklist created by the TM forum that BT contributed to here. Whilst automation removes the mundane jobs, it does have an impact on human expertise. If we're not careful, we can have a result where automation leads to no one understanding how the network works. We'll have no experts. And expertise will be required to fix the automation when it breaks. and it will break. Humans will have direct inputs into the autonomous networks, either via training the artificial intelligence or actually in the closed loop to build confidence the automation works or to prevent it going seriously wrong, so long as we have the experts, of course. There's some things that are more difficult to automate than others. For example, conflict resolution and multi-party negotiation. We have to understand where we are going to manage the risk associated with automated systems, and how are we going to manage that risk. And finally, automation should result in organizational transformation, impacting culture and process, regulation and control. Automation may render historic approaches unsuitable, for example, length of network contracts. So in conclusion, autonomous networks are a journey, but should we start from here? Is the design of the network, systems and process appropriate for automation? Robustness comes first. The automation must be robust. Autonomous networks are model-driven. Who maintains those models? Standards models, are there too many or not enough? A dual domain expertise is required to build autonomous networks, so one must understand both networks and modeling. Autonomous networks are part of a bigger framework of changes in the industry, such as NFV and SDN. Autonomous network designs must capture externalities. Machine learning will be useful for autonomous networks, but has well-known issues. And finally, autonomous networks will still need human experts. Thank you for listening.
Thank you very much, Peter. Peter will now be taking live Q&As, so please do put your questions into the chat box function on the Swapcard platform.
Okay, thanks, Milad. I can see some good questions coming in from Vadim. So what's your real use case of machine learning? So I flicked through the slides very quickly, and I'll just talk you through some other things that we've already got going. Of course, cybersecurity. So we're already using machine learning to visualize cyber events. So that's something that we're already using, and we've got a product out there that some BT customers, our corporate customers, are using. We've been using machine learning for workforce management for a long time. So that's optimizing essentially the traveling salesperson issue. You know, how do we get the right engineers to the right place and optimize that? So we've been using machine learning in our workforce management for quite a while now. Network planning, of course, optimizing the network design, that's uses machine learning as well. Recently, we've launched BT Call Protect that uses machine learning to block nuisance calls. It learns what nuisance calls are and then blocks them in the network. And of course, like many organizations, we're using machine learning in marketing. So, you know, understanding how to prevent churn, detecting where it might happen, and doing active marketing to stop that churn, and up and cross-selling, of course. And we've also used machine learning in BT Care, where monitoring customer engagement via Twitter. So those are all real things we're using machine learning for right now. That's in service and been really useful to BT. The other question, a much more difficult question from Vadim, is how do you solve a problem of creating models for different models for different vendors? Yeah, that's one of the real key issues is when we take on board a new vendor, who's providing the model. I suppose there's some assumption that the vendor will bring appropriate models with them. But of course, I suspect those models will be just a baseline that will need some work by BT or by a system integrator to integrate them into BT. So, for example, the vendors' models may be missing some basic information that our systems need, so that would have to be added to the model. So, yep, there's always work to be done. I think it would be a baseline from the vendor, and then either BT or the system integrator would have to take those and make it work. are you able to train network models into productive network? Yeah, another good issue that we're currently looking at. How do you train models? And of course, models that learn from essentially trial and error. So as in some machine learning approaches are really difficult and risky to run in a live network, because it does a trial and it's an error, and then you're impacting service. I mean, some of the projects we've looked at, I've tried to use simulators to do that, but then you're very dependent on the accuracy of your simulator. If you trust your simulator, you can run your machine learning on the simulator, and it can do the trial and error on the simulator. And we've used that model, and that model works in theory, but any assumptions or errors in your simulator will end up working their way through to production. So there's definitely a risk with that approach as well. How do I feel about closed loop automation? Oh, thanks, Milad. Yeah. I think it's essential. It's essential to autonomous networks. You won't get autonomy without it. And again, there's already some examples. You could consider things like OSPF, routing protocols today, for example, as a form of closed loop automation, where it's monitoring the status of links and it updates the routing according to the real-time status of those links. It's essential. I think when you get to more complicated things, like things we're researching right now, how a human expresses an intent, some sort of service, you literally ask the network what service you want, and network interprets that and monitors the status, and if it's not meeting the SLAs that are agreed, it adapts. Something much more complicated like that, I think, is a real challenge. Today, I'm seeing fairly simple closed loop automation, like in Kubernetes. The traffic load increases, you need more CPU, you can increase the number of instances or the amount of CPU allocated to a task. That's relatively simple, but even that simple thing has issues with going in the opposite direction. At what point can you start shutting CPUs down and shutting processors down? And that's related to the management of state. So I think there's a lot of challenges in closed loop automation of the more complicated use cases, especially when the state to be managed, and that's just going to require much more research. And I see some lots of work going on that. I think we'll get there eventually. It's certainly key. Have I missed any questions? No, those were all very good questions. So thank you for those questions.
Peter, we have one more, I think, which came through from Robert Curran. Is BT working with different partners, suppliers than traditional ones, or relying more on in-house R&D?
Yep. So we're definitely working in a collaborative fashion. So, for example, one of the projects we have is what we call a prosperity partnership, which is 50% funded by BT and 50% by the EPSRC, which is a government agency in the UK. And we're working with a group of universities, which includes Lancaster, Bristol, Surrey and Cambridge universities, in this next generation converged digital infrastructure project, NGCDI. There's a web page out there if you Google it. And that's an example of, we gave them the challenge of think what networks will look like when we started the project in like 10 years time. How extensive, think of how extensive the scope and the size and the importance is going to be of that network, and how will we run it in an autonomous fashion. So they've been doing a lot of very interesting research there. So that's one example. I mentioned another example earlier on, which was the Horizon 2020. So BT has participated in many Horizon 2020 projects, and right now we're also participating in some Celtic projects that are looking into this space. So that's with universities and enterprises, and small and medium enterprises as well as large enterprises across Europe, essentially in this space, network automation. And of course, we have some of our own in-house R&D as well. So yeah, a wide range of engagements there across the industry.
Thank you, Peter. I think we're just about run out of time, but Peter's session will be on demand for the next 30 days, and I'm sure Peter will be around at some points today to be able to answer any questions that pop up in the chat function.
Yeah,